It's my pleasure to introduce you to Seyda Ipek from UC Irvine. She is a UC President Fellow. She studied in the University of Washington with Ann Nelson, did a postdoc Fermilab. Her research spans topics including neutrino masses, dark matter, and the antimatter asymmetry. She's going to tell us about how a dynamic QCD constant can alter early universe cosmology.
Thank you very much. Yeah. Well, thanks for inviting me here, first of all. Although the weather was not too nice. Yeah, today I'm going to tell you about the problem of generating the baryon asymmetry of the universe. And let's start with the problem or the quantification of this quantity, basically. So we can kind of observe that we are all made up of matter, and not just us, but all the stars, galaxies, the interstellar medium, everything we can observe is made up of matter instead of antimatter. And there are a couple ways to quantify this asymmetry, meaning the asymmetry between matter and antimatter in the universe, and two instances in the history of the universe to measure that asymmetry, basically. So the quantity that tells us about this asymmetry is this called the baryon to photon ratio, or the baryon to entropy ratio. Is the difference between the number density of baryons, and when I say baryon, you can just think about protons or neutrons, photons and neutrons. And so this is the difference between the number density of baryons in the universe minus the number density of antibaryons divided by the number density of photons. And sometimes it's given in terms of by dividing into the entropy density. But let's look at the baryon to photon ratio. So this number can be measured at two distinct times in the history of the universe. One of them is from the cosmic microwave background. This is basically just CMB, and the number you measure from the cosmic microwave background is 6 times 10 to the minus 10. So this is the amount of the asymmetry that exists in the universe. And the same quantity can be measured also at the time of Big Bang nuclear synthesis. So the CMB measurement is done when the universe was about 400,000 years old. That's when the photons last gathered. The the Big Bang nuclear synthesis happened when the universe was about a second old. So it is much before the CMB, but you expect to see the same number basically. So here this is a plot of this quantity eta, baryon to photon ratio, and y-axis is the abundance of elements that were produced at the time of Big Bang nuclear synthesis. So these are the first elements in the universe that was produced, and their abundance in the universe depends on the matter-antimatter asymmetry. This purplish bar is the measurement from CMB. This is 6 times 10 to the minus 10, and these yellow bars are the measurements of the light elements. And you can see, or maybe you cannot see, because it is extremely well measured. The deuterium abundance matches really well with the measurement of the asymmetry from CMB. The helium 4 abundance also agrees with the CMB measurement, but the error bars are much larger. The lithium abundance doesn't agree that well. There's a 2 sigma problem called the lithium problem, but I won't talk about that today. So, but overall, this quantity is measured very well to be about 10 to the minus 10, or 6 times 10 to the minus 10. So this number, or this 10 to the minus 10 number, kind of corresponds to an asymmetry between quarks and antiquarks in the early universe. Of basically, you need to have one extra quark for every 10 billion quark-antiquark pairs that you have. So having that one extra quark at the end gives you a matter-antimatter asymmetry of 6 times 10 to the minus 10. And in order to produce this asymmetry from a particles physics model, you need to satisfy 3 conditions called the Saccharo conditions. And this is basically any particle physics model that you have to explain the universe needs to satisfy these conditions to produce an asymmetry, a matter-antimatter asymmetry. So the first condition is that the baryon number needs to be baryon number cannot be a conserved quantity, so it needs to be violated. And I will go into more details of these conditions. So the second condition is that charge and charge parity symmetries needs to be violated. CP is basically a way to differentiate between matter and antimatter, so it cannot be a conserved quantity if you want to make a difference between matter and antimatter. And the third condition is that there must be some out of equilibrium process, or some process needs to be out of thermal equilibrium. This is because in thermal equilibrium, you expect any process that's happening in one direction happens in the opposite direction at the same rate. This is kind of definition of thermal equilibrium. So if you have a process that is producing baryon number, it would also erase that baryon, or erase that asymmetry basically, but you don't want that to happen, so you need to be out of thermal equilibrium. You need to have some process that happens only in one direction and does not happen in the opposite direction. And of course, the first condition is because we assume that the universe started in a matter and antimatter symmetric way, so the number of matter and antimatter was equal, and so you want that number to be violated so that there's some asymmetry produced along the way. So these are the three conditions, and when you have, let's say these are the rules of producing matter-antimatter asymmetry. When you have the rules, the first question we ask is, does the standard model satisfy these rules and can it explain the matter-antimatter asymmetry? Because standard model is a very good model explaining many things in our universe. The first condition is actually satisfied in the standard model. Standard model, the super title is giving you the answer, but the first condition is actually satisfied. The baryon number violation exists in the standard model. This is because weak interactions involve only left-handed particles and not right-handed particles. So this generates an anomalous current. This is the baryon current here. It is given by the trace of WW2. W is the field, SU2 field strength and the dual of it. So this quantity or this violation happens via what is called instanton processes at zero temperature. So let's assume that our universe is stuck in a potential like this. This is just a cosine potential. At zero temperature, it is just sitting, and this is the x-axis is baryon number or the baryon asymmetry, and this is some energy. At zero temperature, the universe can sit in one of the minima of this with some baryon number. And in order to change baryon number, it needs to tunnel. And tunneling is a very stressed process. It is stressed exponentially, actually. So in the standard model, this tunneling process, the rate of this tunneling process is about e to the minus 160. It is a very small number. This is why we don't expect to change the asymmetry we have right now is kind of stuck in, basically. So we don't expect it to change because of this suppression. But at very high temperatures, especially at temperatures above about 100 GeV, which is called the electroweak scale, the universe can sit closer to a maximum of this potential, and instead of tunneling, it can kind of just roll over the potential. These rolling solutions are called sphalerons solutions or sphalerons processes. They don't have this exponential suppression. They can happen in thermal equilibrium, and their rate goes like alpha weak to the 5. Alpha weak is this the electroweak coupling constant times T to the 4. So at high temperature, this is to say that at high temperature, the standard model is actually very efficient at violating baryon number. Even at zero temperature, it does not, baryon number is not violated. Which is good because the baryon asymmetry can be produced just at the very early universe when the temperature was higher. And furthermore, standard model also has CP violation, again in the weak interaction sector. We observe the CP violation, we can measure it. It comes through a phase in what is called the quark mixing matrix or CKM matrix. However, for technical reasons, which we can talk about later, the CP violation in the standard model is not enough to produce the observed baryon asymmetry. So if you do a back-of-the-envelope calculation, it can only give you an asymmetry of 10 to the minus 20. And remember, the measured asymmetry is 10 to the minus 10. So the standard model CP violation is 10 orders of magnitude smaller, basically, than what we need. And the third Saccharo condition, the need for a process that goes out of thermal equilibrium is definitely not satisfied in the standard model. There are no out of equilibrium processes. So overall, even though standard model has baryon number violation and CP violation, somewhat CP violation, it cannot explain the observed baryon asymmetry of the universe. And this is one of the strongest reasons why we need some physics beyond the standard model in order to explain the baryon asymmetry. And we know that this new physics model requires new sources of CP violation, and it requires an out of equilibrium process. And this new physics has to interact with the standard model because at the end you want to produce the standard model protons and neutrons and standard model particles basically. So you need some interaction between the new physics and the standard model, which is a good thing because if there is some new physics in our universe, we also want to observe it, and the only way that we probe new physics is through its interactions with standard model particles. And of course, when you know what you need, there's also a lot of models that, tell you that they have what you need. So I try to categorize models of baryon asymmetry production here. This is definitely not a complete categorization, but just gives you an idea of what is available in the theory sector. So a set of models, these are called electroweak baryogenesis models. They just add new scalar fields in the standard model. These are basically new Higgs bosons or Higgs fields. And what happens when you add a new scalar particle into the standard model is that the transition from a Higgs field of 0 vacuum expectation value to non-zero vacuum expectation value becomes a first order phase transition. And a first order phase transition happens via an out of equilibrium processes. And furthermore, when you are adding a new Higgs boson, it can also have CP violating interactions, both with the R Higgs boson and with quarks. So that just gives you extra CP violation. And these are generically called electroweak baryogenesis models because they expand the electroweak sector basically. And the baryon number violation comes from the electroweak sphalerons processes. Another set of models are called leptogenesis models. These do two things actually. They both explain why neutrinos are massive via a right-handed neutrino, and that right-handed neutrino can decay into standard model particles via an out of equilibrium process, meaning that they decay when the temperature is lower than their mass, and their decays can have CP violation. So this addresses, the leptogenesis models addresses two problems at the same time. And another way to explain the baryon asymmetry is kind of sweeping it under the rug, saying that there's another thing that we don't know in the universe, which is what dark matter is. So say that there's some dark sector that explains dark matter, and it has its own asymmetry, which is then transferred into our universe. And you can explain why the dark matter is asymmetric, or you don't need to explain it. You just need to explain how it is translated into the standard model particles. And these are generically called asymmetric dark matter models. There is also a set of models called Ipek and Baryogenesis. And but overall, there are lots of models to explain the matter-antimatter asymmetry of the universe. And some of these, so all of these usually just expands the electroweak sector of the standard model. A different approach is actually looking at strong interactions instead of the electroweak interactions. And this is a path less traveled. So one thing that that might excite you or people about the strong sector is that it also could have its own CP violation. This is a possibility because there is an allowed term in the QCD Lagrangian. It's called the theta bar GG dual, where G is the strong field. G is the gluon field tensor. And so this is allowed. And if you can write this term, at some point it generates a CP violating observable called electric dipole moment for the neutron or for quarks, and then it translates into a neutron electric dipole moment. And this dipole moment is proportional to the CP violating term theta bar. And you can go ahead and try to measure this dipole moment to see if there is any CP violation. We've been trying to measure the neutron EDM for decades now. We haven't observed it yet. This is a plot item from Wikipedia. This is the upper bound on the neutron EDM over the years for different experiments, basically. So the upper bound, there's an upper bound because we haven't observed it yet, so you can put an upper bound on theta bar. So the bound is getting smaller and smaller, and right now the neutron EDM bound is about 10 to the minus 30 active charge times centimeter, which translates into a bound on the size of theta bar, which is 10 to the minus 10. So 10 to the minus 10 is a small number. So theta bar is a dimensionless quantity. And particle physicists have a notion that dimensionless quantities should be order 1. If they are very small, we would like to have an argument for some like mathematical argument or a symmetry argument for why they are small. For example, if that number was 0, is there a symmetry that you restore, for example, so that the smallness is due to some symmetry breaking. So the smallness of this number is called the strong CP problem. Again, the problem is that because it is so tiny or maybe 0. And one solution to this problem was introduced in late 70s by Petrie and Quinn, and they did come up with a symmetry argument for the smallness of this number. They basically promoted theta bar into a dynamical field. So this theta bar effective is basically a field called the Axion and how it behaves in its potential. Potential defines what the value of theta bar is. For example, it can be very large at some early times in the universe, but then as this Axion field rolls down to its minimum, theta bar goes to 0. And this again tells us how much CP violation there is in the strong sector. And it was later realized that this Axion field could also act like dark matter. So it again like solves kind of two problems in one go, which is still very exciting. And there are several different experiments for QCD Axion. So this is a nice thing. This is both telling you that there can be some large CP violation in the early universe in the strong sector, but we don't expect it to see it right now. And CP violation is one important ingredient of explaining the matter-antimatter asymmetry. However, the strong interactions do not violate baryon number. They couple to both left and right-handed quarks. And there's also no out of equilibrium process in the strong sector. So the other two conditions of the Saccharo conditions are not satisfied. But we will come back to the phase transition in a bit, basically. So this is kind of the reason why strong interactions are not expected to be involved in, or were not expected to be involved in generating the baryon asymmetry of the universe. However, this is what I told you is more like the standard model QCD, and we can expect, or at least speculate, that QCD was different in the very early universe via some new physics, basically. And you can play this game with the early universe because, unfortunately, the earliest observations of early universe is done at the time of Big Bang nucleosynthesis. This is again when the universe was a second old. And before then, we don't have any observations, so we don't know what happened, basically. The universe could be very different than what we expect it to be, and we wouldn't know. This is a curse and a blessing. Of course, we want to know. But so if you don't know, there's a nice playing ground that you can come up with new histories for the universe, basically. So this is where we started. It's like, so we said, since we don't know anything what happened before Big Bang nucleosynthesis, is there a way to change QCD actually before Big Bang nucleosynthesis, and what would that do? So the QCD, so it is already expectedly different than what we have right now in the early universe because of the running of the QCD coupling constant. So this is again just a standard model. So at 0 temperatures, this is a plot of the strong coupling constant versus energy or temperature. So at very low energy, strong coupling constant is very strong, it's much larger than 1, and that's why quarks are bound into inside the proton. Quarks and gluons are bound inside the proton, and that's why we call it strong interactions. However, as you raise energy, strong coupling constant actually becomes smaller. It becomes so small that quarks are no longer bound to the proton above a temperature of 1 GeV. So they are expected to be in a plasma state, and they are not bound into protons. So this transition from weakly interacting to strongly interacting is a phase transition. And in the standard model, this transition happens at a temperature of 1 GeV. The QCD actually has many more phases. This is the phase diagram for baryon density versus temperature. So at very, very early universe, the temperature is very high. So the quarks, and again, quarks and gluons are not bound into protons. They are in a state called quark-gluon plasma. And as the temperature becomes smaller, they bind into hadrons. They bind into protons and neutrons. And there are other states, for example, at high baryon density, there's neutron star, and there are states called color, flavor, locking states. But this is a very complex phase diagram, which is a very fertile and current area of research, basically. But what we are interested in for the early universe is just very close to this axis, very small baryon density and this high temperatures, basically. So this is, in this diagram, these lines are called lines of first order phase transition, meaning that to change from one phase to the other, you go through a first order phase transition, which ends at a critical point. And this here, you see that there's no line separating the two phases. This is because in the standard model, the transition from quark-gluon plasma to the hadronic phase is expected to be a crossover, meaning that there's no actual phase transition that separates the two. And there are theoretical and computational reasons for why that happens in the standard model, that you have a crossover. This is because our quarks are too heavy. This is another phase diagram. This is here, the x-axis is up and down quark masses presumed to be equal, and the strange quark mass. This is not from Lattice. This is more or less theoretical arguments. So if the quarks are very light, meaning light compared to the QCD scale, or compared to the scale where the transition happens, you expect a first order phase transition actually. But our standard model lies here, where the strange quark mass is too heavy, so such that this transition is a crossover transition. So again, theoretical and computational arguments tells us that if you have 3 or more light quarks in the strong in QCD, you would have had a first order phase transition. Similar is true for very heavy quarks. Actually. If you have very, very heavy quarks, you also expect a first order phase transition when changing from a quark-gluon plasma to the hadronic phase. So this would have been very exciting, but again, in the standard model, you don't expect this. But how about going some beyond the standard model, basically? So so my work with Tim Tate at UC Irvine, in our work, we said, let's try to change the QCD coupling constant in the early universe. And you can do this by just coupling things to the gluon field strength. And here we are just looking at a new scalar singlet, S. It is reduced by some scale m star. And the singlet has some complicated dynamics in the early universe, which then gives you a dynamical QCD coupling. So instead of just a number GS here, you have a QCD coupling constant that depends on the value of the singlet S. And this is similar to the Axion, what Axion does for theta bar. But we are not coupling to GG dual, we are coupling to GG, so that this is actually the QCD coupling constant, not the theta bar term. So when you do this, so if you haven't done this, so this is again the same plot of QCD coupling constant versus temperature. Here, this purplish, the straight, not straight, but what do you call this? Unbroken line is undashed. Solid, yes, solid. I know words. solid line is what would have happened in the standard model. You know, the QCD coupling constant just runs with energy and becomes strong at a temperature about 1 GeV. However, if you just change the value of the Signet field, this is Vs is the vacuum expectation value of the Signet field, which I will come back to, you can give another contribution to the QCD coupling constant, which then just changes where it becomes strong. So by changing the field, the vacuum expectation value of the Signet field, you can make the QCD phase transition to happen at a few tens of GeV or a few hundreds of GeV. You can even make it a few TeV basically. And I should also define this quantity called the QCD scale, which is basically the energy scale when the QCD coupling constant becomes larger than 1. So this basically, for standard model, the QCD scale is about 1 GeV, and for these different values of the Signet field S, it can be tens of GeV or hundreds of GeV. And it depends on this quantity Vs over m star. This is basically just a Signet field that acquires a vacuum expectation value in the early universe. And in order to have that vacuum expectation value in an interesting way, the most basic potential for the Signet field we could come up with is this. So this is the H is the R Higgs boson, and S is the scalar singlet, and it has some couplings to the, it has some mixing with the Higgs boson. So this is the scalar potential that we will be interested in, and we will analyze. But what will happen is that the new scalar sector, including the singlet, will have some very interesting dynamics in the early universe, which then affects the QCD sector, and then it will at the end produce the baryon asymmetry for us. But let's start with the dynamics of this new universe with the scalar in it, basically. I want to give you a comparison of the two thermal histories, one for the standard model and one for this new universe with this nice singlet in it. So in the standard model universe, you expect that at very high temperatures, especially at temperatures above 150 GeV or so, the Higgs field vacuum expectation value was 0, so all the particles were massless. And at this temperature of about 150 GeV, there's an electroweak transition where the Higgs field acquires a vacuum expectation value, and the gauge boson, the electroweak gauge bosons and fermions become massive. And the universe continues to cool down, and at about 1 GeV, QCD quarks confine into protons. So this is the standard model universe. Of course, there's a lot more things happening in the meantime, but the points that are important for today's talk. So in the new universe, there will be many more phases and points of importance. So at very, very high temperatures, the two universes are the same. So they're both Higgs value is 0 and Signet value is 0. At some point, this Signet acquires a vacuum expectation value. And we will see later that for certain parameters in the Signet potential, when you come to 150 GeV in a standard model, you would have expected that the Higgs field acquires a vacuum expectation value, but for us, Higgs will still stay in 0 value. So even though you are below 150 GeV, Higgs value is still 0. And at some temperature Tc, QCD will confine, and this Tc is much larger than what you would expect at the standard model. And QCD confinement will trigger the Higgs to acquire a valve, basically, which then triggers another transition into a deconfined phase, or normal QCD. The field goes to the standard model value, and QCD deconfines again. But this phase, this new phase of QCD confinement at very early universe is a very interesting period. If you look at it more closely, what happens is that in this confined phase, there are no quarks, there are hadrons. So the finite temperature corrections to the scalar potential is much different as well. But again, to look at the transition pattern here, there's kind of a three-step three-step transition where first you are, so this is the Higgs field and the Signet field. You first go to a Higgs 0 S finite state, and then both of them are finite, and then you go to the standard model where Signet field has 0 web and Higgs field has the standard model value or the value that we observed now. Of course, to understand all of this, you need to look at the finite temperature scalar potential and find, when the transitions happens. This is a complicated process, but the part that is about QCD confinement, or the part that is that you have usual gauge bosons and quarks, have been studied extensively. This is a normal finite temperature corrections to a scalar field potential. The new part that we did is the corrections from a confined QCD phase. Again, this is different because now you don't have quarks, but you will have mesons and.
So what's the typical value of that wave scale, like DS?
Right, I will come to it, but it's about TeV, a few hundred GeV and TeV basically.
Between 150 GeV and the TeV.
Sorry, what?
Between 150 GeV and the TeV, somewhere.
Yes. Okay. So, right. So as I said, above QCD confinement, your degrees of freedom are quarks, and your finite temperature corrections come from quarks. But below confinement, you don't have quarks anymore. You only have, let's look at mesons. You only have mesons and hadrons. And in this scheme, so since we are looking at a scenario where this confinement transition happens when all of the quarks are massless. So the spectral breaking pattern is actually SU6 cross SU6 to SU6 diagonal. So this is just like left and right-handed quarks going their diagonal, the SU6 diagonal form. And this can be, kind of characterized by this chiral Lagrangian. We can discuss till the cow comes back from border, if this Lagrangian explains everything, or if you can write down this Lagrangian for a non-perturbative state. But let's assume that the chiral Lagrangian has all the information that we need. So this matrix U is the pion mass matrix. It has the mesons we require. F pi is the pion decay constant, and kappa is a parameter that describes the mass of your pions. This is done and can be done in for normal QCD as well. In normal QCD, we usually have just like pi plus, pi minus, and pi 0. But here, due to this breaking pattern, you have 36 mesons. So for simplicity, we just put all of the Yukawas except the top Yukawa, we set them to 0, and we only keep top Yukawa, which then gives us only 10 massive mesons, and the other 25 are massless. Okay, and the masses of the new mesons. So again, in the standard model, you expect a very different meson spectra, but in this one, so the massive mesons are just given in terms of this the parameters in this Lagrangian, basically. And you can theoretically write this down, but at this stage, you don't know what this quantity kappa or f pi is. These are just not. Your Lagrangian doesn't tell you what they are. We need to measure something to find what they are. And in the standard model, we know these quantities from the pion mass and measuring the pion decay constant. And you can draw similarities between this new phase of QCD and the standard model QCD. So again, in the standard model, you can find this kappa 0 is the standard model values, and phi 0 is the standard model value just from measurements, and then kind of make arguments to see what they would be in this new phase of QCD. So up to corrections that come from having 6 massless quarks versus 2 or 3 massless quarks, the quantity kappa scales by the 3rd power of the QCD scale, and f pi scales with the 1st power of QCD scale, whereas the pion mass scales 1 power of the new QCD scale and the quark masses or the Higgs. So this is just scaling arguments to kind of know what the new meson masses will be. For example, if the new lambda, so the standard lambda QCD is 1 GeV, if the new lambda QCD is 100 GeV or 1 TeV, F5 will be 100 GeV or 100 times F50 or 1,000 times F50, and so on and so forth. Okay, so now when we know the meson masses, you can calculate what is their contribution to the finite temperature potential. But beyond the meson contributions, there are other contributions to the finite temperature scalar potential. First of all, you have a typal contribution from the meson mass term. This is basically coming from a term like this in the potential. So you have the Higgs boson. So technically, you have the QQ bar term. This is what gives mass to the quarks. But now these quarks are confined, so you have a typal term for the Higgs. You also have mesons in thermal loops, which is this the second term here. And then you also have a term that comes from the Signet Field when the gluon also has a condenser in the QCD, in the confined phase. So these are the three new corrections, or three new contributions to the scalar potential that comes from this new phase of an early confined phase. I mean, technically, this exists for the standard model Higgs as well, but this is very small compared to other contributions to this potential. Here it could be large. And when you have the potential, and I haven't showed you the potential, the finite temperature potential about confinement, but you can put all of them, and you can find the minimum of the potential at various temperatures. And this is what we do. Again, the zero temperature potential is given here. The parameters A are the Signet potential parameters, and B1 and B2 are the parameters that govern the mixing between the Signet and the Higgs. And of course, there's a lot of new parameters. These 5 plus, you can set the QCD scale and what M star is. So we set all of them to certain values to kind of look at one benchmark for this potential, because it's easier to do. So I will just give you what the set parameters are at the top of the potentials and look at the potential at different temperatures. So this is high temperature, T equals 200 GeV, so like above the standard model electroweak scale. And but below when the Signet has valve. So with these parameters, the minimum of the potential, or the global minimum of the potential is here, where the Higgs valve is 0, and here we set the Signet valve to 1.5 TeV or minus 1.5 TeV. We change this parameter for different benchmarks, but this one is 1.5 TeV. And in all of the potentials that I will show you, the red dot will show you the global minimum of the potential. So this is at very high temperatures. You are at a symmetric phase in the electroweak symmetric phase, and your Signet has a valve. As the temperature gets lower, especially when it falls below 150 GeV or so, there is the global minimum actually changes. So the global minimum is here, where the Higgs has a standard model like valve basically. So even though this is the global minimum, this potential has a barrier between these two minimums. So our universe was stuck here because there's a potential barrier separating the two minima. So the universe actually is stuck in a metastable state for a certain amount of time because this barrier is too high and the tunneling is stressed a lot. So this is an interesting phase, and whenever there's a dragon, it will also correspond to a barrier, basically separating the two minima. As the temperature falls at a critical temperature, here with these parameters, it is at 85 GeV. So this is when QCD confines, because the strong coupling constant became strong enough, and that confinement tilts the potential in the Higgs direction. So now the Higgs valve equals 0, minimum actually disappears. Now there's a minimum at some finite Higgs valve. still the global minimum is at a standard model-like point. However, the barrier persists. So the barrier is still separating. So this minima, you can only kind of roll to this new minima, but you cannot tunnel into the global minima. So the universe is still stuck at a metastable vacuum, even though it is a finite Higgs back. So this is the QCD confine phase. Of course, below this temperature, basically, now we don't have quarks, you have mesons, and you have meson contributions. And what those do is, as the temperature gets smaller, this minima becomes, it gets lifted, so it becomes higher and higher, until when it's not a minimum anymore, it disappears, and then the universe just rolls to the standard model-like vacuum, basically. So this is a very multi-step transition, and I find it fascinating. But the overall, so this is an instance at 2 MeV. This transition actually happened way before 2 MeV, but 2 MeV is a nice temperature to check because it is when the Big Bang nucleosynthesis happened, and you kind of recover a standard model-like vacuum before Big Bang nucleosynthesis. So again, this transition happened much before 2 MeV actually. So this is the multi-step potential, and again, the potential I showed you is given for very specific values of these parameters. We looked at many other values of the parameters. So for that, so we have six benchmark scenarios where we change A1, A2, A3, and A4. Sorry, A2, A3, A4, and we vary B1 and B2. Again, B1 and B2, as you can see, are the mixing parameters, mixing complex between the Signet and the Higgs. So this plot is very crowded. I will tell you what these blue and pink regions, the shaded regions, correspond to, but in a bit. But right now, it is the only important part is the dark gray and the lighter, lightish portions, basically. So in this region, the nice transition I told you from rolling to this standard model-like vacuum actually does not happen. That barrier never disappears, so that the universe would have been stuck in a metastable vacuum up until the end. So you don't want to be in this stage. So the larger Higgs Signet couplings are a bit dangerous. So, but in this lighter region, that transition always happens before Big Bang nucleosynthesis, and even though it happened, you wouldn't have observed it basically at Big Bang nucleosynthesis. So you want to be in this whitish region.
So, but this S square, these are the masses for these new particles.
Yeah, so the masses for the Signet field are these dashed lines here. You can see MS, this is 18 GeV, this is 16, so it will be in actually between
so you want, there is no collider constant?
Oh yeah, I will come to that. Yeah. This is a very good question. The answer will be, unfortunately, not yet, because the mixing is very small. Okay, good.
Because they have blue coupling, right?
Yeah, so I will come to that as well. Yeah. The mass is very small, so the backgrounds are very large. So this is only telling you that even though this new phases and like nice regions, nice phase transitions in the universe could have happened, you still recovered the standard model before Big Bang nucleosynthesis.
Also one other thing, that but the meson spectra you don't see it, like a eta meson.
No. Oh, sorry.
Eta meson, like see you have this S blue.
Yeah. So in right now, no, because again, like even like LHC, the singlet doesn't have is at 0 well basically. So you are not. Yeah. So you're not doing anything to the QCD right now. It's at 0 temperature basically. Even at Rick and stuff, it's not high enough temperature to excite S. So this was this part was just the interesting scalar dynamics and phase transitions and the new QCD phenomena basically. And this new QCD can also do something very interesting for very asymmetry. And I want to, well, as it was the title of my talk, let me tell you how it happens. So this happens because, again, QCD is doing new things in this new history of the universe. One thing it's doing is that it is going through a first order phase transition actually. Because when the QCD confines about when the quarks are massless or when the Higgs value is 0, you have more than 3 massless quarks, which gives you a first order phase transition. And first order phase transitions are very interesting. They happen via what is called the bubble nucleation processes. So it's basically the universe is in a phase of quark-gluon plasma, and when you hit a critical temperature Tc, bubbles of the new phase, which is the hadronic phase, starts forming, and that hadronic phase actually has lower energy, and the universe, of course, wants to lower its energy so that the bubbles start growing, and at some point they fill the whole universe. But this bubble nucleation, depending on the rate of bubble nucleation and some other dynamics at the time, it can be out of thermal equilibrium, or what physicists would call out of thermal equilibrium, meaning that it happens faster than the rate of the expansion rate of the universe. In our case, these bubbles are not only in a hadronic phase, they also in a phase where the Higgs has a non-zero value. So even though it's not the standard model value wave yet, it is still non-zero. And this also has some, it is important because outside the bubble, Higgs has 0 wave. This also means that the processes, the sphaleron processes that I mentioned, which are baryon number violating, happen very efficiently. However, when Higgs acquires the wave, those processes are exponentially suppressed. So outside the bubble, there's baryon number violation, whereas inside the bubble, there's no baryon number violation anymore. And furthermore, as I said at the very beginning, QCD can also have CP violation via the new fields called the Axion. And what the Axion field does when all of this is happening is that at high temperatures, the theta bar quantity or the CP violating quantity is 1, and at the temperature, the critical temperature when QCD confines, theta bar actually relaxes down to its value of more or less 0. So this is what the theta bar or CP violation is doing while the QCD transition is happening. You can also look at the mass of the Axion field. At very high temperatures, the Axion mass is very small, and as QCD confines, it acquires a larger mass, which is also related to the pylon mass. So these are kind of, everything is happening maybe disjointly, but the important thing is that all of these transitions are happening at the critical temperature where QCD is confining. And the one extra, or not extra, but one other component of the story is, of course, baryon number violation. And this all, again, happens if there's a theta bar term. There's a pseudoscalar meson called eta prime, which couples to both GG dual and WW dual. This then gives you an effective coupling between the GG dual condensate and the anomalous baryon current. So this is basically the same quantity that is baryon number violating, and its rate is very high at a phase when Higgs value is 0. And the GG dual condensate generates a chemical potential. So this is basically gives you a barrier between quarks and antiquarks. So it just makes the production of quarks just a bit easier than antiquarks, basically. And the value of the condensate is proportional to the Axion mass and the CP violating term. This is, again, it should be proportional to a CP violating quantity because it is a quantity that makes a difference between quarks and antiquarks, or particles and antiparticles. But this, so from this quantity, you can get to a chemical potential, which is just the time derivative of this quantity, and you can do that with just some going from the Lagrangian density to a Lagrangian. But as I said, what is nice here is that all of these changes are happening at the critical temperature when QCD confines. So this is when basically Higgs value goes to 0, your sphalerons are turning off, and then your theta bar is turning off. So you have very efficient baryon number relation here, and then you just preserve that baryon number relation right below QCD temperature. And when you put in numbers, so as I said, the chemical potential goes like the Axion mass, which is proportional to the pion mass, and your effective Lagrangian has an eta prime mass, which is proportional to the QCD scale. So technically, you know all of these numbers. There's not much actually. There's not much tuning that you can do in a way. The only tuning is what is the Higgs web at this transition, because Higgs web is not at a standard model value. But when you put in all these numbers, you get very close to the observed baryon asymmetry. So the observed baryon asymmetry here is given in terms of the baryon number density over the entropy density, which is about 10 to the minus 10. And with just some order 1 numbers, you get more or less the same number, basically, which is kind of fun. And this is assuming the new lambda QCD is a bit lower than the Curie scale, but not much lower. So this is the baryon number production part of it. But going back to the parameter space, now I can tell you what this blue and pink regions are. Again, you always want to be in this light region because you want to recover the standard model. In the pink region, the Higgs web before confinement is non-zero actually, so the sphalerons are never turned on. So you don't want to be in the pink region because you will never produce a baryon asymmetry because your Higgs web is already non-zero. Whereas in the blue region, Higgs web below confinement is non-zero, but it is still quite small, especially small compared to the temperature. So even though the sphalerons will be exponentially expressed, that expression might not be large enough. So even inside those bubbles I told you, you could be washing out a baryon asymmetry, basically. So this is a dangerous region, but there's an asterisk for it because this is too conservative a bound because we haven't calculated the washout factor, actually. We just put the strongest constraint, which can be too conservative. So we might be able to go more into this blue region. But in this white region, everything works out perfectly, and we produce the baryon asymmetry of the universe. This is for one benchmark scenario. We did 6 benchmark scenarios by changing the quantities A2, A3, and A4. So this is another benchmark. Here, you have a larger parameter space available, basically, and presumably this dark region kind of closes again for larger values of V1, but we haven't gone that far because of it's hard to do, and we had finite amount of time. Okay, so as was asked before, in all of these plots, I'm showing you many lines. One is this lines of the QCD scale, the new QCD scale. They're all about 80 GeV, between 40 and 100 GeV. And these dotted lines are the Higgs web at the critical temperature. And these dashed lines are the mass of the Signet Field S. Mass in now, so at 0 temperature. For the benchmark scenarios we looked at, the Signet Field is always quite light. It is between 5 and 40 GeV or so. And again, it mixes with the Higgs, which gave us this nice Higgs transition pattern. But for that Signet Field, you can also look at this as collider phenomenology. The Signet Field is, it can be produced and decay through both its interactions with the Higgs and also the gluon, with the gluon. So you have this SGG term, which then the thing that can decay to gluons. It can also decay to quarks and leptons via mixing with the Higgs. So for the values that we are interested of M star and the mass, the gluon decays always dominate actually. So here the first plot is the decay width of the Signet Field versus its mass. And the lower plot is the branching fraction to certain final states for different Signet masses. And here theta is not the QCD angle, theta is the mixing angle between the Signet and the Higgs. So you can see the gluon decay width is much larger than other decay bits. So this is different than a generic scalar mixing with the Higgs, because if something mixes with the Higgs, or really any scalar field, usually couples stronger to just heavier fermions. So you expect the dominant decay to be bottom quarks. But here, since you have the gluon channel open, it's actually dominant that decays to gluons almost everywhere, but sometimes bottom quark comes very close. So this is the final states you can kind of think of when you think about looking for the Signet field. And so there are two separate regimes for the Signet field. One of them, if it is quite heavy, you can look at resonant digest searches, which has been done in this paper. But you can see this is Signet mass 2 to 5 TeV. So this puts very strong constraints on that scale m star, which is the scale of the gluon interactions. But for lower masses, this is not as good, if not impossible, because of the background, basically.
There are some constraints from UA1 and all this stuff, like old experiments. Like they have some digest constraints which runs lower.
Goes to smaller. We should talk about it. I would love to know. But this is the only one I could find.
You're taking from LHC, yeah.
This is Axion Mass. Atlas. So Atlas, this is the resonance searches. For lighter singlets, there's an axion-like particle limits, basically, from a recent paper by Gavela and company. This is not resonant though. This is an angular distribution, non-resonant searches, basically. And they put a bound on, again, they have a similar term. It's of course SGG dual, but in terms of final state, this is still gluons. So they put a limit on m star at 3 TeV. However, angular distributions are affected by pseudoscalars, more for pseudoscalars than scalars. So this might not be the correct limit for a scalar.
What's the mass of this?
This is mass is just smaller than 100 GeV. So this, if it is smaller than 100 GeV or so, it is basically mass independent limit. But I am told that the same group is doing a similar study for scalar fields. So I'm hoping that they will have an answer for us. So these are kind of the two searches for gluon final states. Of course, there are other searches for just looking at scalars mixing with the Higgs. So this is a plot for, again, the Signet mass on the x-axis and the mixing angle theta, mixing angle between the Signet and the Higgs. And for some of these points, the mixing angle is multiplied by the branching fraction to BB bar, because some of the searches are looking for specifically for BB bar final states. Of course, this is only available if the Signet is heavier than a BB bar resonance, so it's only if it is heavier than 10 GeV or so. So this is there are limits from Opal at lab, which is final state independent. So this limit actually goes all the way down to small Signet masses. But there are also lab limits which look at BB bar final state, so they are cut off at 10 GeV. So, but these two searches, they only constrain the mixing angle at about 10 to the minus 2. And on this plot, the dots here are the 6 benchmarks that we studied, again, which give you the correct Baryon asymmetry and which allows you to return the Signet model before BPN. So these blue dots are what works, or what the white region corresponded to in our benchmark models. You can see none of the parameter spaces we found are constrained yet by experiments. But there can be future, for example, Higgs or Z factory. You could hope to observe this, such small mixing angles, basically. And but for a Signet smaller than 10 GeV, it is mainly decaying to a gluon final state, and we couldn't find any constraints or even future constraints. And I will be happy to discuss discuss opportunities basically to look for a light singlet that is, that has blue-blue interactions. It would be fun. One other possibility is that, again, these are mostly looking for BB bar final states, but this, so one opportunity here is that the singlet can be produced via gluon fusion as well. So its production cross-section could be larger than what you expect from a normal scalar. So you could hope to win from some, raising the production cross-section and look at final states that have a lower branching fraction, for example, lepton final states. So even though the leptons are much lighter than BB bar, so their branching fraction is much smaller. For example, here tau is much smaller than a BB bar branching fraction, and muons would be even smaller. You can expect just gaining some cross-section from this gluon interactions basically, and that would be a fun thing to look at. And again, we haven't done that study yet. So hopefully our grad student will be interested enough that she will write a UPair code and will run MathGraph and all of that for us. But so that's one thing that we want to do. The other thing is, of course, expanding the parameter space, because we only looked at 6 background scenarios, and one would hope that you populate all these empty regions as well, which would be interesting to see if there's a pattern or not. And I know I went through a bit fast in terms of the QCD phase transition and also the baryon asymmetry production, and that's because the transition here, the QCD phase transition and the bubble nucleation, all of that is happening in a strongly interacting plasma, and this is not well understood yet. So it will be actually nice to understand how, for example, bubbles nucleate in this case, and that will probably affect the production of baryon asymmetry as well. Which is also important for actually, if you think of, for example, gravitational waves, which are expected to be produced at first order phase transitions in the early universe. So, and this phase transition falls into a temperature regime where it is expected to be seen at future gravitational wave detectors like LISA. However, the spectrum of the gravitational wave for this scenario is not known, because again, it is not a weakly interacting. This is actually everything is strongly interacting. So you can come up with arguments why bubbles will be, very similar to other things, but these are just theoretical arguments. And so that's also, again, the understanding the phase transition or the bubble nucleation is important for learning about the gravitational wave spectrum as well. And the one other thing that we are currently thinking of is how are generic dark matter scenarios affected if there is a phase of confined QCD in the early universe? Like, you can expect that the dark matter annihilation will be maybe cut off because now you have heavy mesons instead of massless quarks. And maybe next time I visit, I will have more to say about that. And also the UV completion, the effective interaction that I gave you, the S over M star GG, that is an effective term. This is expected to come from some complete UV model. We haven't looked into it, we haven't thought about it that much. I know it can come from, for example, dilaton will have similar interactions, or you can expect maybe there are some heavy vector quarks and then you just integrate them out and that gives you the SGG interactions. But when you have some more UV complete model, you might also expect more phenomenology that comes along basically, and that will be fun as well. There's a lot to do.